Okay. So this is the assignment one of this course: atomic absorption spectrometry, trace and ultra trace analysis of metals. So this course is instructed by Professor J.R. Mudkavi, IC Bangalore. So let me start with the first question. This is basically I will be discussing some basic questions, basic objective questions related to the introductory part of this course only. So the first question says that the procedure for environmental pollution control involves. So these are the steps given here. You have to identify the what are the basic steps for the control of environmental pollutions. First is the determination of pollutants and extent of pollutions. Second is the technical intervention, and third is the post intervention evaluation. So first of all, you have to know the meaning of this determination of pollutants and extent. So, in which at what extent the pollution is there, and how to determine the pollutants. So, in the technical intervention, you can see which are the available methods. What are the available methods for determination of these pollutants, and after their quantification, or basically you can say the post intervention evaluation. So you can say all of these can include in the procedure for environmental pollution control. Okay. The next very easy questions, basic question: the electronic radius of the atoms are order of, the all you know about it is a few angstroms. Okay. First of all, I will be discussing some basic question, and after that I will be discussing some numericals related to this course. Okay. Yes, the neutrons are stable. You have to see the are stable in the nucleus or outside the nucleus, in the reactors or in the environment. So can you, this is basic question, let me know from the candidate. So you can type the answer for this. Neutrons are stable in. Okay. So neutrons are always stable in the nucleus. What is the reason? So first of all, you have to know what are their the interaction or their binding force, exchange forces. So neutron and protons are held together by very rapid exchange of nuclear forces, called into play by this rapid exchange of pi mesons. So the you can see, so these the exchange as pi mesons particles. So the mass of the exchange particle decide the range of the forces. Okay, so this is basically the weak force that binds proton and neutron inside the nucleus. Okay, so for most details, you may read this article published in the published by Nature Communications. Okay. Yes, the electronic excitation energy for visible and UV ranges lies from, these are the ranges basically the given in kilocalories. Okay, first is 1 to 35.71 kilocalories. So you have to calculate the energy. You can use simply this formula, and these two values are already known to you. Lambda, if I go for the visible range, you can easily see 400 nanometer to 800 nanometer for visible range, and UV is 200 to 400 nanometer. Okay, if if I talk about the energy for this wavelength, this will be minimum, and for 400 it will be maximum only for visible range. If I talk about similarly for UV, the maximum energy for this, the maximum energy will be for this wavelength and minimum for this. Okay, so try to calculate. Okay, and use the formula this. Just calculate and let me know what the answer you are getting. Okay, Himanshu is typing the answers. So you can solve the expression for energy also. Kindly let me know what the value you are getting. Okay, let me solve it. So the E will be, Planck constant will be 6.6 10 to power minus 34 joule second per mole, and the velocity of light will be 3 into 10 raised to 8. And if I calculate for lambda is equal to 400 nanometer. Okay, so it will be like this. Okay, meter per second. So you can easily calculate 6.6 into 3 divided by 400. It will be 10 raised to minus 3 8 plus 9. Okay, let me use the calculator. That will be get 0.0495 10 raised to minus 70s, right? Joule per mole, you can say. Okay, so convert into kilocalorie. First convert into calorie. Okay, so divide 0.495 4.18 into 10 raised to minus 17. 0.0118 calorie, or okay, let me clear it. You can follow the simple conversion, like you will be getting. You have to just divide 10 raised to 3, and you will get 0.0118 into 10 raised to minus 20 kilocalorie. Okay, but the values here is 35.71, like that. Okay, so what you can do, you can this value you are getting in point, sorry, 0.118 into 10 raised to minus 20, okay, kilocalorie. If I convert uh, per mole to kilocalorie only, so I have to multiply by Avogadro number. Okay, 0.0118, 0.071 into 10 raised to 3, or you can write it 71 kilocalorie. Okay, this is for 400 nanometer. Okay, if I will go to 800 nanometer, it will be just half. Okay, so it will something 35.5 kilocalorie. Okay, so this will be the minimum value. Similarly, for you can calculate for UV range. Okay, that is 400 nanometer. Okay, so you will be getting this answer, 35.71 to several hundred kilocalories. Okay, you have to use only the basic formula. uh, yeah, no, 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 I got the answer only joule per mole. Yes, yes. Hmm. Yes, joule second. Yeah, yeah. Meter and, yes, meter and meter, this cancel out. Okay, and second will also be cancel out by meter per second, this velocity value. Yes, yes, per mole. Yeah, if you want to calculate it for per atom, okay, there are Avogadro number in 1 moles. If you want to see the number of atoms in 1 mole, it will be equal to Avogadro number, right? So you can easily calculate by Avogadro number, or you will get the value only in kilocalorie, right? Okay, okay, okay. So should I go to the next one? So the neutrinos have mass and positive charge. This is just an elementary particle. Uh, it has mass and positive charge. It has mass and negative charge. It has mass and no charge. So I think you already know that. You, A, mass and positive charge. Neut- Mass and no charge. I think this table you can see here. So this is the neutrino. There is no mass, no charge. Okay. Yes, 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 yes. Absolutely, you will get in NPTEL portal. There is a separate section called interactive session. Okay, you will go there and you will get the folder for these PPTs and the YouTube video link also. Hmm. Soft copy, I think I have to check that. Okay. At my end, I can say that you will get all these PPTs, which I am taking the interactive sessions, and these video links you will always get. And in the next session, I will confirm that you will be getting those PPTs also or not. Okay. Okay. So these are the elementary particles. You have to just remember the notations and mass, charge, and the relative charges. So basically, neutrino is a fermion elementary particle. Fermion is basically which obeys the Fermi Dirac statics. That is a matter of different thing with a spin of that interacts only by the weak interaction and gravity. So this is basically the definitions of this neutrino. So, the nuclear stability is already when we talk about the neutron proton ratio. Okay, so how nucleus attains this high neutron proton ratio? Okay, so the question is asking high neutron proton ratio in atomic nuclei attain stability by radioactive decay process. So, what is that decay process? It is beta emission. Okay, you can say the beta decay, neutron emission, positron emission, and proton emission. Okay, just try to give the answer, and after that I'll explain. Yes, Himanshu, are you there? Okay, no, 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 it will be beta decay. Okay, the famous reaction, the I will explain. Okay, this is the beta decay. Okay, so you can see this carbon 14, 6 carbon 14 is converting into 7 nitrogen 14, and it is uh, radiating one electron plus one antineutrino. So if I calculate here, here is the number of neutrons is 8. Okay, and here is 7. Okay, and proton is in this case proton is 6, and in this case proton is 7. Okay, so one proton is increasing here, right, and one neutron is decreasing. Okay, that means one neutron that is reducing is converted into proton, one electron, and one antineutrino. Okay, so maintain that charge, we have just write this electron, because proton and neutron will make the charge neutral. Okay, so this is the beta decay reaction. So stability in terms of what we, how can we say this nucleus is gaining stability? If you see the, if you see here, neutron proton ratio is 8 upon 6. It's something like 1.3. Okay, and here if you see neutron proton ratio is 1. So what the nuclear stability statement says, if you are getting the neutron proton ratio is close to 1, then the nucleus is stable, right? Yes, sir. So in terms of that, the beta decay is responsible for that reaction. For more details, you can follow this below link, and you can read more about the beta positive decay and beta. Himanshu, can you mute yourself, please? Okay, so you can follow this link, and you can more read about beta positive decay or beta negative decay. Okay, so this is also the questions based on the property of electrons. Okay, so electrons cause, first is the ionization in gases, second is the darken the photographic plates, and third is yield X-rays when bombarded against suitable targets. And the last one is the all of these. Okay. Yes, yes, D. And can you just tell me in which phenomena you can observe the ionization by electrons? Any idea? Okay, okay, no problem, no problem. So ionization in gases. If you uh, read the mass spectroscopy, okay, so there will be a parent molecule, basically the parent gaseous molecules. Okay, when it is bombarded by electrons, it will further fragment it into more ions that will that are called daughter ions. Okay, and it is the parent ion. So electron can also cause the ionization in the gases. Okay, one phenomena. Third, you can see if like in X-ray diffraction, we can use any metal surface. Okay, metal surface. So if I bombard the electron in the metal surface, they will emit X-rays. So basically, this is the phenomena for generation of X-rays by the introduction of electrons. So it is also the phenomena that electrons can darken the photographic plates. So all of these will be the right answer for this. Okay. So the spectral line series exhibited by Lyman, Balmer, Paschen, Brackett, and Fund holds true for. So these are four options. You can try first, and after that I will explain. So basically, these five lines are observed for hydrogen-like molecule. Okay, this is week one assignment. Yeah, have you not read these spectral lines in the first week lectures? Okay, 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 okay. No issue, no issue. But you can just try on the basis of your previous knowledge. You can just try, and I am here only to explain. Just one second. हाँ क्लास में मैसेज डाल हम्म ठीक Are you getting? Or should I explain? Okay. So the spectral line are basically firstly observed for the hydrogen. Okay. So if you see the case of hydrogen, one S, one H, it is the electronic configuration of hydrogen. So only you have to observe the same electronic configuration, and you can say yes. Uh, these spectral line series can be exhibited by others also. Okay. Yes, yes. Yes, from periodic table, I will explain. Okay, helium plus. Okay, so the molecular atomic number is 2. Okay, if I write the electronic configuration, that is 1s2. Okay, and if I write for helium plus, it will be 1s1, right? Because one electron is ejected. So this configuration is similar to hydrogen, right? And similarly for lithium plus 2, that is atomic number 3, if you write the configuration, that is 1s2 2s1. Okay, and if Li plus 2, okay, this one electron is this, and second one is ejected from the 1s. So you will get the similar pattern for this lithium plus 2 also. So you can say this spectral line will be exhibited by the option second. Okay, is it clear? Okay, okay. uh, yes, 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 yes. Okay. So this is the numerical type question. If lambda max is this angstrom, then wavelength of second line of Balmer series will be. Okay, so you have to find out the just wavelength of second line. First of all, you have to know what is the Balmer series. Okay, in the spectrum of hydrogen, you will see if it is n is equal to 1, n is equal to 2, n equal to 3, n equal to 4, n equal to 5. Okay, so if you getting the transition n is equal to 1, nee, sorry, 2 3 4 5 dot 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 infinity to n equal to 1, like this. Okay, so this will be called the Lyman series. Okay, and if you are getting similarly, if you are getting the transition of this electron from 3 4 5 6 dot dot infinity to uh, n equal to 2, right? Like this. So these will be called the Balmer line, right? Balmer line. If you are getting the all the transitions are uh, if the electron is emitting the some kind of energy and returning to the second this orbit having the quantum number n equal to 2, so then it will be called the Balmer series. Okay, so in this question you have to find out the wavelength of second line of Balmer series. So what will be the first line? It will be 3 to 2. Okay, and what will be the second line? 4 to 2. So we can say the n1 is fixed, that is 2, and n2 will be 4. If it was the first line, it look like this. Okay, so you have to find the wavelength of this transition only. Okay, so just try. Oh, okay, so write the simple formula. Okay, 1 upon lambda is equal to r, that is the Rydberg constant. 1 is 1 minus n2 square. Okay, just try these calculations and tell me what the answer you are getting, please. R is the Rydberg constant. Okay, the r value is 13.6 electron volt. If you read about the complete expression, okay, so you will getting like this, minus r upon n square, that is a Rydberg constant, and its value is calculated as, this is the constant basically, you will getting 3.6 13.6 electron volt. Okay, So just put the values of n1 and n2 here, and tell me what the answer you are getting. 1 upon lambda is equal to 1 upon n1 square and 1 upon n2 square. uh, 2.55. You have to select all these options only. One is 16 by 3r. Do not convert into decimal. Okay. Only fractions. Yes, yes. Yes, lambda. Have you got the answer? Yes. Solve it. 4 minus 1. So it will be 3r by 16, and lambda will be 16 by 3r. Okay. So have you understood that numerical? There is no use. Only for confusion purpose, lambda max is given. And one information you are getting from lambda max is, uh, okay, if you see E is equal to hc upon lambda. Okay, so where the lambda will be max, okay, energy will be minimum. Okay, and the lambda max will be if you are talking about the transitions. Okay, so in which case energy minimum will be n equal to 3 and n equal to 2, right? So in the question, the value for n equal to 3 to n equal to 2 transition is always already provided, right? You have to just calculate the second line. If let's say if any questions, in any question, if anybody asks you what is the use of lambda max here and what is the use of calculation of the second line, you can say I have already the lambda vex value for these transitions. Okay, I have to calculate the wavelength of second line for second Balmer series only, second line of Balmer series, right? So this is only for confusion. Okay, so this is another question you can try by yourself. Here for particular okay, so the wavelength emission radiation emitted is lambda naught when an electron jumps from third to the second orbit of hydrogen atom, that is n equal to 3 to, for this transition you are getting the lambda value is lambda naught, right? For the electron jump from the fourth, that is fourth to second orbit, you have to calculate the lambda in terms of lambda naught, right? So okay, okay, just calculate. I am waiting. Have you reached till this step? Okay. Have you got the option B? Hmm. So just divide lambda by lambda naught. So R will be cancelled out, and you will be getting 20 by 27 lambda naught. Okay, fine. Okay, so I am going to the next one. So if the R is the Rydberg constant for hydrogen, you have to find the wave number this time of the first line in the Lyman series. Okay, the first line will be n equal to 1 equal. This one will be the first line. Okay, so 1 upon lambda R. Okay, so you just have to find the wave number. Wave number is 1 upon lambda, that is 3r by 4. The second option will be the right answer. Okay, yes, yes, 1 by lambda. Okay, uh, wave number is just see, if you know this expression is equal to h nu, right? Yes, so you can expand nu is c by lambda, right? Okay, so if let's say if I am observing some variation e with respect to lambda, it will be a reciprocal. Okay, have you got my point? What I explained? 1 by 2 and 2 by 9. So let me check. I will solve it. Okay. Upon lambda is r, that 1 minus. Yes, yes, yes. No, 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 no. You have to do it for individuals. Like you, like, yes, yes, yes. Lyman largest to sort, and second is bracket largest to shortest. Okay, you can try. 1 by 3. Okay, okay. Let me just check. So lambda is equal to 1 upon r, and in another case it will be uh, 1 minus 4, that will be 3 r by 4, that is 4 by 3 r. So it will be 4 by 3 r and 1 by r. It will be 4 by 3, not 3 by 4. Yes, yes, you just do the river. How much? 3, 3 only. Okay, just this means a new slide here. Okay. For bracket, it will be okay, and equal to 2 Lyman bracket. Bracket will be n1 is equal to 4, right? No, no, no. It will be for bomber. Yes. N1 will be 1 for Lyman, then bomber, then Passion, then bracket. Okay, so the ground state will be N1 is equal to 4 for bracket, right? So, the transition for largest wavelength will be n2 is equal to 5 to n1 is equal to 4, and the minimum wavelength transition will be n2 is equal to infinity to n1 equal to 4, right? Yeah, okay, okay. So you can easily then, following the same procedure, you can calculate the ratio for this. Okay. Right. Okay. So the next question is, the electronic transitions in molecules are characterized by excitation from. Okay. Before doing this question, you should know what are the bonding orbitals, what are the non-bonding orbitals. Okay. So if I am saying the molecule contains carbonyl group, okay. So this pi bonding will be called the bonding orbitals, and oxygen have lone pairs, right? So these electrons are not participating in the bond formation. That's why they are called the non-bonding electrons. Okay. So every bonding orbital has their anti-bonding orbital. Like, and these are represented. Like, say, if I'm saying this pi orbital, okay, so its anti-bonding orbital will be pi star. Okay, so if you know about the bond order, basically we define the bond order by 1 by 2 bonding orbitals minus anti-bonding molecular orbitals. Okay, so this is the bond order formula, right? So here the non-bonding orbitals, non-bonding electrons, sorry, are not taking place in the bond formation. Okay, so the transitions in the molecule are characterized by the excitation from. Okay, so this slide is for this particular question. What you can see, the if I draw the energy levels, so the ground state will start the sigma orbitals, that is single bond, then pi, then non-bonding orbitals. Okay, and after that it's anti-bonding orbitals, and similarly for sigma star. Non-bonding doesn't have any anti-bonding orbitals. Okay, so this is the basic uh, phenomena. Okay, if I talk about the transitions, so these are the allowed transitions. You can see the sigma to sigma star transitions, n to sigma star transitions, pi to pi star. These all are the allowed transitions in any molecules. Okay, you have to just remember those transitions. Okay, if I am talking about what is the feasibility. Okay, so if I am talking about this transition, that is sigma to sigma star. Okay, so you can see here there is a very large energy gap between sigma and sigma star, right? So you have to provide the larger energy value for doing these transitions. So we can say this transition is energetically not allowed, but symmetrically it is allowed. Symmetrically means if I am talking about this sigma bonding orbital, it is g-red orbital. Okay, and the sigma star is un-g-red orbital. Okay, and what the Leporti selection rule says that the g-red to un-g-red uh, transition is always allowed. Okay, so because symmetrically we can say these are allowed transitions, but energetically not allowed. But these are the basic transitions you can see in the molecules, or you can see for the you can use it for the characterization purpose. Okay, so you can see here this transition is bonding to anti-bonding, this is non-bonding to anti-bonding, this is also bonding to anti-bonding, and this is also bonding to anti-bonding. So sorry, so you can say the third one will be the right answer, because every molecule is characterized by its bond order, its stretching frequency. Okay, so the bonding orbital to anti-bonding orbital transitions are characterized by these excitations, right? For more details you can see the UV spectroscopy. Hmm. To anti-bond. Yes, 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 to anti-bonding, because in the two bonding is just repeat that. Hmm. No, no, there's two non-bonding is not possible, but two bonding and two anti-bonding are also possible. Yes, yes, yes. Uh, I will explain to you. Okay, if you like say if you know the p orbital has three subsets, that is px, py, and pz, right? Right. And p orbitals are always overlap side by sides, and they are responsible for pi bonding, right? Okay, so if I am saying this is pi 2px, or say let's say yes 2px, and I'm saying it is pi 2py, right? And it is pi 2pz. Okay, so this pz symmetry can only bonding with s orbital, because this pz and s orbital has same symmetry, so they can make this hybridized orbital spz. Like, okay, if you are having two orbitals, then that is first is pi 2px and pi 2py, they will be of same energy, right? So you can say the molecules is having two pi orbitals, one is pi 2px and one is 2py, and accordingly you can feel the electrons, right now. Right, similarly this pz will make the sigma bond. Okay, so it will be sigma sp jet like, because this is not making a pi bond, it is only making the sigma bond, right? And these two will make the pi bond, so that's why it can have two pi bonding orbitals, right? Okay. So the last, yes, yes. Pi bonding to pi anti bonding. Yes, pi star. Because let's say if you are having water, okay, there is no pi bond, right? So if I want to know the bond order, what is the bond order between oxygen and hydrogen in water, you will say one, right? Na? So the water molecules are having only the sigma orbitals, right? There is no pi orbital, but the water has oxygen only. Oxygen has lone pair, that is the non-bonding orbitals, non-bonding electrons. They can also enter to the sigma star anti-bonding orbitals. So you can see there you can observe n2 sigma star transitions also, right? Because if you are saying then why pi cannot enter the sigma star, right? Because there is the symmetry difference between two orbitals, so these transitions are not allowed. Yes. Yes, that can also happen. Sigma to sigma star is hmm. Yes, there is not going to be any pi to pi star transitions. In carbonyl, you can observe pi to pi star transition. So molecules are characterized by only these bonding orbitals. Okay, like this thing. Hmm. Hmm. Yes. Yes. No. That. Hmm. Yes. No. That will be going to the emission spectra. That will be not the absorption spectra, na. Okay. This is, yes. I am talking about absorption. Only in the case of absorption, you will see the bonding to anti-bonding orbitals. And if you are interested in to know the emission spectra, you will go for the fluorescence spectroscopy. That will show you the emission transition. That is phosphorescence, fluorescence. Okay, that will be the emission spectra. Here I am talking about the absorption. Yes. Yeah. Yes. Absolutely. Uh, I think AES spectroscopy related course is not there. Atomic emission, X-ray, X-ray fluorescence. Yes, you can read X-ray fluorescence. Yeah, I should. I have to check. I have not seen the course related to XRF, but there must be some characterization course covering this XRF technique. Like you can say the advanced characterization technique course, you can observe the XRF. Okay. So and the last question is you have to just tell me the Bohr circular orbitals are the extension of Sommerfeld elliptical orbital. This is the true statements, false statements, or sometimes true, sometimes false, and has no relationship with each other. How? Yes, 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 yes. Bohr model has that. But you can see in the theory, uh, circular orbitals are the special case of these Sommerfeld elliptic orbitals, right? Like say, if I am drawing here a circle, okay, this the Bohr, like say, it is Bohr circular orbit, okay, and if I am drawing this Sommerfeld elliptical orbital. Let's say this is the major axis, this is the minor axis of this ellipse. Okay, and nucleus is in the center of this circle, but on the foci of this ellipse, right? Right. If if I am interested to know the ratio n equal to k is equal to length of this major axis and length of minor axis. Okay, so if I took the major axis and minor axis are same, so it will be formed to a circle, right? Correct. So the Bohr circular orbits are the special case of Sommerfeld elliptical orbital. So this is always true. Okay, a principal quantum number, azimuthal quantum number. You can read the theory related to this Sommerfeld elliptical orbital, and you will understand all these terminology. Okay. Hmm. Hmm. Yes, it only in one case only, but only this one case is only the Bohr's theory states that the electrons are revolving around the nucleus in a stationary orbits. That is called Bohr orbit, right? So if I am saying Sommerfeld is a union, okay, and the Bohr circular orbitals are the part of it, okay, so it will be always true. At which condition it will be false? I'm saying only this statement that Bohr circular orbitals are the extension. I'm not saying that the atom will always follow the Bohr's atomic theory instead of Sommerfeld elliptical theory. Hmm. Uh, it will become the Bohr's model, right? Yes, it is extension, right? So I have explained, I think, all the problems for this assignment. If you are having any problem, you can type me in the chat box. I will explain. Okay. Rest assured, you can get these PPTs. Okay. And if you are having any doubt, you can just go to the discussion forum of this course and type the question. I will answer there also. So I will be recommending one is for basic atomic orbital theory, you can read any of the inorganic chemistry book. For atomic absorption spectrometry, you can refer to the fundamentals of an analytical chemistry book by Skoog, West, Holler, and Krauss. First, okay. So first, what you do? First, you have to read the notes given in the form of PDF as the website of this NPTEL course. Okay. After login, you are not getting any PDFs. YouTube videos are there only, right? Okay, okay. I will try to talk with the course coordinator, and let's see. I can. What can I do? Okay, okay. If there will be any problem, you can post the question to discussion forum. I will answer there also. Okay. Uh, so I am now disconnecting. Right. Okay. So thank you for attending, Himansu. You can leave now. Okay. Oh, okay. 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 Thanks. Yes. Yes. I will definitely try for it. Okay. Thanks.